Good evening, one and all. Myself Yashvi Sheth, and let's start with the 8th live session of the course Basic Principle and Calculations in Chemical Engineering, taught by Professor Subrato Majumdar. I will share my screen. So let's start with the 8th live session. So in this session I will take you forward in the concepts of energy. So previously we had talked about what is the meaning of energy, and what different forms of energy are related with any process. How is energy very important to any chemical engineering, in chemical engineering, and for any system, how do we apply energy balance when it does not have any chemical reaction. Sorry for the disturbance. So if it does not have chemical reaction, then we had taken into consideration what type of energy balance is obtained. So I will just write that equation for you. So general energy balance for any system can be written as accumulation of energy in the system is equals to input of energy to the system minus output of energy from the system. This is when there is no chemical reaction. Otherwise there will be two terms for generation of energy and minus absorption of energy or consumption. So we had studied kinetic energy, which is represented by half mv square, which is nothing but the energy related to a moving body. Then we had studied about potential energy, which is nothing but mgh, which is nothing but the energy stored when we keep an object away from the driving force in the opposite direction. So it is the amount of energy that will be stored in the object. We talked about internal energy, enthalpy, work, heat, etc. We also talked about Bernoulli's equation, which is nothing but a kind of energy balance represented by delta P plus V square by delta P by rho V square by 2 plus G delta Z equals to C. It has to be delta V square. So this is nothing but Bernoulli's equation when you have to apply energy balance and how is pressure related to the flow energy and potential energy. So now this was all about energy calculations and understanding the energy when you have just phase changes or you just have no reaction. We also studied about energy like sensible heat when there is temperature change, and we studied about latent heat for increasing the temperature and for phase change. So this we all have already done. Now moving forward, if you want to like in any chemical industry, you encounter with the systems where you have chemical reactions, and for any chemical reaction there will be certain heat transfer occurring, or there will be certain change in energy is observed, like the for in for any reaction to occur, you might have to supply the energy or you might have to extract the energy. For example, you must have observed that like if you dissolve NaOH in water, then there will be certain amount of energy released. And how do you observe this? By increase in temperature. So this is just an example where there is no chemical change, but this NaOH is dissolved, and this is nothing but heat of dissolution. So similarly, if there are certain reactions occurring in any chemical industry, which is the most common reactor is very basic in any chemical industry. So there will be certain energy changes observed during that process. So how do you do the energy calculations for that such a system? So we need to understand what are the energy transfers or changes in energy observed during the reaction, and that can later be used for design of reactor. So for example, if there is heat liberated during the system, then we need to take out the heat from system, because otherwise the temperature will rise, and the temperature can go like up to where the reactor pressure will be affected such that it may burst. So or how much energy should be supplied. So or like also if you want to take out the heat, then in the form of you will use water circulation or some chillant for taking out the heat. So how much flow rate and at what rate you need to take out, all these should be known, and for that you need the data of what amount of energy is changes observed during a chemical reaction. So starting with the basics of this, the basic term for this is heat of formation for any reaction. Now when standard comes, so standard means it the heat of formation or any heat is calculated at two conditions: a temperature equal to 25 degrees Celsius and pressure equal to 1 atmosphere. So if any of the heat change is calculated at these conditions, then any of such property is said to be standard. So if I want to measure heat of formation at this conditions, then it is standard heat of formation. Now what is standard heat of formation? So say for example, there is NaOH, or let's say CO2. Okay, so if I want to prepare CO2, then this is the product, and I will prepare in such a way that like I need to write its elemental constituents. So carbon, one atom of carbon reacts with one molecule of oxygen to form one molecule of carbon dioxide. Okay, So if you write equations in such a way, so the enthalpy change associated with the formation of 1 mole of compound at these standard conditions from the elemental states. Now what does elemental state means? Carbon usually can be taken in the form of solid, or like graphite is the natural form of carbon, so you can say graphite for example. Just a second. Okay, now for oxygen, it is usually present in air in the gaseous form. So elemental constituents or natural form of oxygen is gas. So if I mix this two, if I react these two, then what will be the amount of energy that will be either generated or consumed? So whatever the change in energy you will observe for this type of reaction, then in that case that delta H naught is nothing but known as standard heat of formation, represented by a subscript F, and standard notation is denoted by a naught symbol at the top. So such type of, here you need to take care that for any elemental constituent like for carbon or oxygen that usually occurs in nature, then for them the del H is considered to be 0. The heat of formation for such elements is 0. So it will make the process of calculating the heat of formation easier. Now so such reactions are actually not occurring. So what we do, for any chemical reaction of the form A moles of A reacting with B moles of B, giving C moles of C and D moles of D. So for such a complicated reaction, if you want to find the standard heat of reaction, like since we want to find out for any reaction, then the heat change associated will be known as heat of reaction, and at standard conditions it will be known as standard heat of reaction. Now it will be denoted by delta H of reaction at standard condition, represented by naught, is equals to, so what you will do, so here delta H F naught of any species I is in joules, or it can be in kilojoule per mole of that species. Okay, so it is the this much amount of kilojoules of energy will be released for formation of 1 mole of that compound, because in the definition itself of the standard heat of formation 1 mole of compound is formed. So if I have C moles of C chemical or element, then for, let's say C has delta H F C naught, this is the standard heat of formation for C. So if I have C moles of such constituent C, component C, then in that case C into delta H C naught has to be done. So now since these are in products, so you can consider here any reaction as an equation, which is nothing but A plus B equals to C plus D. So whatever on the right hand side, if I want to take on the, like if I want to make it to 0, then it will be C plus D minus A minus B. So similar algebraic operation you need to do for calculating standard heat of reaction. So since I have C moles of C, then I need to multiply C with the standard heat of formation of C, which D for D. Now these to be added, because these much amount of energy will be produced during the reaction, because C and D are produced with this much amount of moles. Now since A and B are consumed, the energy that will be disappearing from the system will be nothing but A into delta H A naught, and similarly B will be also consumed, so B into delta H B naught will be consumed. So this is nothing but the standard heat of the reaction which is mentioned here. So yeah, this is how you can write any standard heat of reaction for any system or for any reaction. Now there are many reactions in which what happens is, say for example this reaction, or you can simply write as A plus B gives C plus D. So there instead of the reaction taking in one step, the reaction can be further divided into many steps. Say for example A will give me A intermediate, B will give me B intermediate. Now A star plus B star will give me AB star, and this AB star will get again dissociated to form C plus D. Now all this reaction will have certain amount of energies, because energy associated, because it has to overcome this barrier for like if this is the intermediate form, then it has to overcome this much barrier, and this will be the heat of reaction in this case. So so any reaction or any reaction can occur in multiple steps. So we just need to consider the overall reaction in this case. So all these reactions can be summed up, because we will be able to look into this much only. Now there can be reactions where say for example in which the reactions can be numerically or algebraically added. So in that case, so whatever be the delta H of reaction, so for that you just need say for example A plus B gives C plus D, and now you have C plus D gives E. Okay, so the reaction, this is reaction 1 and this is reaction 2. It has delta HR1 naught, delta HR2 naught. So now since your final product is E and you are allowing infinite time and you individually know the heat of reactions for both the reactions, so what you can do, you can just simply, to find out the heat of reaction for this system, what you can do is you can algebraically add these two reactions. So how can it be done? As I said, since A and B are consumed, so this is positive, the product is always said positive and it is said negative. So this will also be positive, this will be negative. So if you take C and D, like here it is consumed and here it is formed, so what you can do, net it will be nothing but A plus B gives E. So for this reaction, delta H reaction naught is equals to delta H R1 naught plus delta H R2 naught. So this will be the net amount of heat change or heat change or enthalpy change associated with this overall reaction. So you just need to take the algebraic summation of C, or there can be some n number of reactions, so you just need to take the algebraic summation of reaction. Okay, so the way you add and subtract the reaction, in that manner you need to add or subtract the heat of reaction. So such law is known as Hess law, which states that if a set of reaction can be manipulated through a series of algebraic operations to yield a desired reaction, then the desired heat of reaction can be obtained by performing the same algebraic operations on the heat of reaction of the manipulated set of reactions. So as I have stated, for reaction 1 and reaction 2, since I have added both the reactions, I will add these two heat of reactions. Okay, so otherwise if I am subtracting two reactions, then what will happen? Say for example, if I am subtracting, then it will be delta H R1 naught minus delta H R2 naught. So now moving forward, all that I was talking about was at standard conditions. Now for any industry, the reactor is not always operating at the standard conditions, which is at T equals to 25 degrees centigrade and P equals to 1 atmosphere, because like the operating conditions in the reactor, it depends on like the nature of reaction and also the economics, because operating at like there will be some reactions which require very low temperature, because economics is how related, because kinetics of the reaction is the important term here, because at higher temperature, as the temperature increases, the rate of reaction is increasing, but there are chances in some reaction that as the temperature is increased, the equilibrium of the reaction shifts at the lower conversion. So in that case you need to optimize like where should be the operating point, such that the kinetics and the equilibrium point are balanced, such that the cost of product is minimum. So you need to have certain like you always operate a reactor at a certain operating condition, which is not always this standard condition. So you need to have the value of heat of reaction at operating conditions. So to find out the heat of reaction at operating conditions, what you do, you just use the heat of reaction at standard conditions. So for example, if this is only the reaction A moles of A plus B moles of B giving C moles of C plus D moles of D, so in that case if I want to find out the heat of reaction, so now if I want to find out the heat of reaction at any operating condition, then naught is not to be written. Okay, so firstly there will be certain heat of reaction which is at standard state, so you always have standard heat of reaction. Now you add the amount of heat that is related to the for example, instead of 25 degrees Celsius, the reaction is occurring at 40 degrees Celsius. So now A moles of A and B moles of B will be taken to the reactor at 40 degrees Celsius, and C moles of C and D moles of D will be taken out of the reactor at 40 degrees Celsius. So so for that, what you will do, so you consider that the reaction, like you will take reactants from 40 degrees Celsius to 25 degrees Celsius. Okay, so for that you calculate the amount of heat change. So that this is nothing but delta H, let's say. Now you perform the reaction at 25 degrees Celsius. So this is nothing but reaction, and you again take 25 the product at 25 degrees Celsius to product at required temperature. Let's say here it is 40 degrees Celsius only. Reactant and product should have same temperature. So this is delta H2, this is delta H1. So since you are like, this is the pathway, so heat is nothing but additive. So you are taking from 40 degrees Celsius to 25 degrees Celsius. Now since this heat will be negative because you are removing, you need to remove certain amount of heat, so this has to be negative. So subtract delta H1. Okay, now you are performing the reaction at 25 degrees Celsius, and the heat associated with the reaction at 25 degrees Celsius is nothing but delta H reaction naught, like, which is nothing but standard heat of reaction. Now certain amount of heat will be generated if you take 25 degrees Celsius products to 40 degrees Celsius. Okay, so that much amount of heat should be added. So delta H are 2. Now since the products are generated, we add the heat, and since reactants are removed, like they are consumed, so we subtract. Now this is for 1 mole. Now if you have n number of moles, so what you do, so in that case, say for example you are having a process, component 1, component 2, component 3 and component 4. These are product, these are reactant. So how will you write the heat of reaction? It is nothing but delta H reaction, like standard heat of reaction, plus product. So for product, so for, let's say 1 mole of N1, these are the number of moles associated, N3, N4. So N3 integration T reference to T final, because I need this temperature change. So T reference is nothing but 25 degrees Celsius. So N3 into Cp3 dt plus T reference to T final N4 into Cp4 dt. Now these needs to be added because these are generated. Now since reactants are consumed, I will subtract that much amount of heat. So T reference to T final N1 Cp1 dt minus N2 T reference to T final Cp2 dt. Now here if this is the initial number of moles, then you need to write delta N, which is nothing but change in number of moles. Moving forward, there are certain reactions where you burn a chemical. So if any reaction, usually it is like for combustion is for organic molecules. So for any organic molecule, if it is combusted, then in the presence of excess of oxygen, then there will form CO2 plus H2O, or CO can be formed as CO also if this is partial combustion. This I had already mentioned earlier. So if it is a partial combustion, then CO will be formed because the supply of oxygen is limited. Now if it is complete combustion, then CO2 will be formed. plus H2O plus. If there is sulfur, for complete combustions SO2 will be formed, and for nitrogen NO2 will be formed. So all these products are for complete combustion. So this is a complete combustion reaction. And if I want to find out the heat of combustion at standard conditions, which is nothing but standard heat of combustion, then what I will do, so similar to the way in which we found out heat of reaction, we will find out heat of combustion. So heat of combustion at standard state is nothing but delta HF CO2 naught plus delta HF H2O naught plus delta HF SO2 naught delta HF NO2 naught minus delta HF of organic compound. So this is how, like, it is nothing but, for oxygen, since it is 0, this is how you write CO2, like products minus reactant, the standard heat of product minus standard heat of reaction. So for any heat of reaction at constant volume, it is nothing but the internal energy change of the system, while at constant pressure it is nothing but the enthalpy change of the system. Now let's start with the assignment. So first question is the heat of reaction in an exothermic process. So I had talked about the heat of reactions. Now the delta H of reaction, or the standard heat of reaction, it can be positive or it can be negative. Now positive, what does that mean? Product minus reactant. If I subtract, then energy is positive, which means product has more energy, this has lesser energy. So for more energy of the product to have, they will take up a certain amount of heat, which is nothing but change in the heat of reaction. So product minus reactant, since it is positive, so that much amount of heat will be consumed such that the product will have more energy. So now if I have any reaction going on, now if product consumes more and more energy from the system, the temperature of that system tends to go down. Okay, so what you do to maintain a constant temperature during the reaction, which is mandatory, so what you do, you supply certain amount of heat by passing steam through this steam jacket or so. So you try to maintain constant temperature for that particular reaction. So if the heat of reaction is positive, then product energy of product minus reactant is positive, which implies that product is consuming certain amount of energy, and which is nothing but obtained by consuming energy in the system, which results into decrease in the temperature of the system. So you supply certain amount of energy. So such reactions are known as endothermic reactions. Okay, and another is when delta H is negative. So product enthalpy minus reactant enthalpy, if this is negative, what it means that the enthalpy of reactant is more, or the heat of formation of reactant is more, which means that more amount product consumes less energy and more amount of energy is released during the reaction. So energy is released during the reaction. Such reactions are known as exothermic reactions. So for exothermic reactions, the heat of reaction is negative. Now if the reaction is exothermic, then as I said, the energy is released. So what does that imply? Temperature of the, now since product is consuming lesser amount of energy, that means that temperature will tend to go upwards. Okay, now as the temperature rises, then it might not be feasible for the reaction. So what you do, this is the cooling jacket, cooling water jacket, where you pass water so that heat will be transferred from the reactor to the cooling water. And here in the endothermic reaction, by supplying steam, you add heat into the system. So both the type of processes are opposite, where one has positive heat of reaction, another has negative heat of reaction. So for this question, exothermic reactions are nothing but they have negative heat of reaction. So I had explained earlier only, if the heat of reaction is positive, then the response is said to be endothermic. So this has to be reaction is said to be endothermic. Okay. Now next question is, calculate the change in internal energy for the following reaction at standard conditions. So let's say this is delta H reaction is nothing but minus 345.68 kilojoule per mole. Now you need to find out that whether this reaction is occurring at constant volume or constant pressure. Okay, so if you want to find out that whether the reaction is occurring at constant volume or not, because if the reaction occurs at constant volume, then delta H reaction is nothing but delta U, which is change in internal energy. Okay, so if I want to check whether the volume, like whether the reaction is occurring at constant volume or not, what I will do, like if I see like volume is usually related to gaseous phase, we usually see, if I check for PV equals to nRT, then what, like pressure is said to be constant here. So if I apply delta of PV equals to delta of nRT, then what remains is delta P is 0, so P delta V, and temperature is also constant, so delta N RT. So if I want to find out what is the change in volume, then I need to find out the delta N of the reaction, which is nothing but change in number of moles. So for this reaction, C2H4 plus 2Cl2 gives me C2HCl3 plus H2 plus HCl. Now since this equation is applicable only for gaseous components, so all the gaseous components only of the reaction should be considered. So here if I apply the mole balance, like which is nothing but moles of product formed, which is 1 mole of C2HCl3 is formed, so 1 plus 1 mole of H2, 1 plus 1 mole of HCl minus 1 mole of C2H4 is consumed minus 2 moles of Cl2 is consumed. So net change in the number of moles delta N is 0, which implies that change in volume is 0 for this reaction. So now when change in volume is 0 for any reaction, which implies that reaction is a constant volume reaction, then delta H reaction is nothing but delta U, or change in internal energy. So here the change in internal energy is nothing but change in heat of reaction, which is minus 345.68 kilojoule per mole. Now moving forward to the next question. The first law of thermodynamics state that energy can neither be created nor be destroyed. So this was already discussed in the previous lectures. So this is the statement, which is nothing but energy cannot be created nor be destroyed. Okay, or the total energy in the universe is always constant, and energy can only be transformed from one form to another form. So the correct answer for this question is D. Next question is, the enthalpy change associated with the formation of 1 mole of the compound at this conditions is nothing but dash. So this is the basic definition for the standard heat of formation. So formation is the correct answer. So enthalpy change for formation. Now the enthalpy change that cannot be predicted by calorimeter can be obtained by dash. So Hess law is the correct answer, because as I had mentioned that Hess law is nothing but if I can represent any reaction in the form of algebraic summation of algebraic manipulation of two or more reactions, then the heat of reaction or the change in heat of reaction is nothing but it can be obtained by similar algebraic manipulation with the heat of reactions as well. So if I am not able to perform any reaction by calorimeter and I am not able to find out the enthalpy change through that, then I can use Hess law and calculate the enthalpy change or the heat of reaction. Now moving forward, if the calculated value of delta H for the reaction is positive, it indicates that the heat of reaction is obviously it is endothermic. So I had discussed the definition many a times in this lecture. So delta H for positive, if it is positive, then it is endothermic reaction. So now again question on Hess law. Hess law deals with dash. So what it deals, it is nothing but we try to find out heat changes for a reaction by algebraic manipulation of number of reactions. So what we do, we try to find out heat change for the reaction or the heat of reaction. So heat change in the reaction is the correct answer. Now next question is, the standard heat of reaction delta H naught for reaction A, for reactants, it has to be reactants, A with B, like for reaction A with B to form C is with stoichiometric coefficients are 1. Okay, so delta H for A, B and C are nothing but A, B and C respectively. So I need to find out the standard heat of reaction. So all these are standard heat of formation. So reaction occurring is A plus B gives me C, and the heat of reaction for A is A, delta H B is B, delta H C is C. So if I want to find out the heat of reaction, delta H naught for reaction is nothing but product minus reactant, delta H naught for C minus delta H naught for B minus delta H naught for A. So it is nothing but C minus A minus B. So A is the correct option. Moving forward to the next question, the standard heat obtained from the bomb calorimeter at 298 Kelvin is dash. The standard heat of combustion delta HC0 of ethanol vapor is as follows. So okay, so standard heat of reaction in bomb calorimeter is given as minus 1363.605 kilojoule per mole. Now bomb calorimeter implies that it is occurring at constant volume. So it is a calorimeter which is used, like this system is used to find out the change in the heat at constant volume. So this is nothing but change in internal energy delta U. So now if I want to find out the combustion in standard heat of combustion, so for this reaction if I check, then delta N is what? Now since H2O and C2H5OH, they both are in liquid, then what happens is I do not need to consider these moles for delta N calculations. So the for gaseous products and reactants, change in number of moles is nothing but NCO2 minus NO2, which is nothing but 2 minus 3, which is minus 1. Okay, so this is not a constant volume reaction, so heat of combustion will not be equal to delta U, which is change in internal energy or the standard heat obtained from bomb calorimeter. So if I want to find out the standard heat of combustion, then it will be nothing but delta H. Okay, so delta H is nothing but delta U plus P delta V. Okay, so this is the general form. Now as I had told you, P delta V is nothing but N, like delta N RT. So I can replace P delta V as delta N into RT. So delta H is nothing but delta U plus delta N RT. So delta U is minus 1363.605 kilojoule per mole. Okay, and delta N is like plus, delta N is minus 1, 8.314 is the unit for R, and T is 298 Kelvin. So this will give me in joules per mole. So to find out in kilojoule, I will do kilo divided by 1000. So now since this is just 1 mole, so I can have it will be per mole. So the correct answer, if I solve this, it will come out to be minus 1366.088 kilojoule per mole. So this is nothing but the enthalpy change or standard heat of combustion, because here you are taking standard heat of reaction obtained from bomb calorimeter. So this is nothing but standard heat of reaction at constant volume. So this will correspond to the standard heat of combustion. Next question is, the change in the enthalpy when the reactants give products under particular condition is dash. So the change in enthalpy when the reactant give products under particular condition is nothing but the heat of reaction, because formation, combustion, neutralization, they require specific conditions. Like there are specific conditions, like 1 mole of product should be formed, or 1 mole fuel, or any say for example CXHY is combusted in the excess of air. So such conditions are not there. So for any given condition, it is nothing but heat of reaction. Next question is, calculate the standard heat of reaction for the following reaction. So to find out standard heat of formation, standard heat of reaction, it will be nothing but delta H naught for H2CO3 minus delta H naught H2O minus delta H naught CO2. Now here, since the stoichiometric coefficients are 1 for each and every reactant and product, so it will nothing but be delta H naught. Here it will be 1. Okay, so it can be written as it is. So if I substitute all the values of standard heat of formation of each of these, then on solving I will get standard heat of formation for this reaction to be 360.139 kilojoule. So substitute these values here, minus 275.2 minus 393.509. so since this is minus of minus, minus 241.83, so this will come out to be 360.139 kilojoule per mole. Next question is, calculate the heat of reaction for the following reaction. So similarly, like as in the case of earlier question, so delta H reaction, now here the stoichiometric coefficient for reactant is 2, otherwise it is 1 for each. So delta H naught for Na2CO3 plus delta H naught for H2O plus delta H naught for CO2 minus 2 times delta H naught for NaHCO3, because 2 moles are consumed and this is in per mole. So if I substitute each and every values, so this will turn out to be, wait a moment, this will turn out to be 135.6 kilojoule per mole. Now here it is in kilojoule per mole, and if I look into the options, they are in kilocalorie per mole. Okay, so I need to have a conversion for kilojoule to kilocalorie. So what is that conversion? 1 kilojoule corresponds to 0.239 kilocalories. So I have already 135.6 kilojoule. Then what will be the corresponding kilocalorie? Then I will cross multiply, so which will be nothing but 135.6 into this much, so it will come out to be 32.41 kilocalorie per mole. So next question is, the sum of internal energies of product and the sum of internal energies of a reactant at a given temperature and at a constant volume, it will be nothing but, so it has to be stoichiometrically added. Okay, so delta H that I am taking, so I am doing delta U product plus delta U reactant. Now if I add this stoichiometrically, then this will be negative. Okay, so which will be nothing but at a given temperature and volume, which means at constant temperature and volume, so it will be heat of reaction at constant volume, because it will be delta U that will correspond to constant temperature and volume. This will be nothing but heat of reaction at constant volume. So find the difference between the heat of reaction at constant pressure and constant volume for the reaction 25 degrees Celsius. So what do I need to find out? Heat of reaction at constant pressure, this represents constant, minus delta H reaction at constant volume. So this is nothing but enthalpy change. This is nothing but internal energy change. So if I write this, then delta H minus delta U I need to find out. So delta H and delta U are related as delta H equals to delta U plus P delta V. Okay. So if I want to find out delta H minus delta U, it is nothing but P delta V. Now applying ideal gas law to find out P delta V. So P delta V will nothing but be delta N RT. Okay. So I will substitute this as, so delta H minus delta U will nothing but be delta N RT. Okay. Now here delta N is nothing but change in the number of moles of in any reaction for gaseous species. So product formed are 2 moles. So 2 minus, there are 3 moles of H2 consumed minus 1 mole of N2 consumed. So delta N is nothing but 2 minus 3 minus 1, which will be minus 2. So delta H minus delta U will be minus 2 RT. So correct answer is option B, minus 2 RT. Next question is, for a closed system, the relations delta H plus delta U plus equals to delta U plus P delta V is valid for which of the following conditions? Okay. So H equals to U plus PV is the basic or general relation between enthalpy, internal energy, pressure and volume of the system. So if I want to find out the change in enthalpy, then change in enthalpy is delta H equals to, I need to apply change for all. Okay, so delta U plus delta of P into V. Now if I want to simplify this, then this will be delta U plus, now this is delta and it will apply to both. So so you will similar to the laws of differentiation, what you will do, you will keep one constant and you will apply delta for another. So you will keep, let's say, volume constant delta P plus P constant delta V. Okay. So here the given equation is delta H equals to delta U plus P delta V. So here they are not showing this term, which means that delta H, like delta P is 0, because V will not be obviously 0. So delta P is 0, which means constant pressure. So obviously this is the definition of enthalpy, which is nothing but the change in energy at constant pressure. So constant pressure is the correct answer and this is the derivation for it. Okay. Next question is, the heat of reaction at constant pressure is nothing but called as, so this is what we talked in the earlier slide, which is nothing but enthalpy. Calculate the value of the difference between heat of reaction at constant pressure and volume for the given reaction. So again you need to find out delta H minus delta U, because you need to find out difference between heat of reaction at constant pressure and constant volume, which is nothing but delta H and delta U. So this will nothing but be equals to delta N RT, as I had shown earlier. So you need to find out delta N for this reaction. Now since H2O and C6H6 they are in liquid state, you will do is for gaseous. So 12 minus 15 will be the value of delta N for this reaction. So it is nothing but minus 3. So delta H minus delta U will be minus 3, 8.314 temperature is 298 Kelvin. So 25 degrees Celsius is nothing but 25 plus 273, which is nothing but 298 Kelvin. So if I do the calculation, then it will be 3 into 8.314 into 298, which is nothing but minus 7432.7 joules. Okay, now since this is in joule, if I the options are in kilojoule, I will divide it by 1000. So my 7432.7 by 1000, so that will give me energy in kilojoules. So answer will come out to be minus 7.43 kilojoule. Okay, so next question is calculate the standard heat of reaction for the following question. So here you need to find out standard heat of reaction. So you need to subtract product minus reactant. Now here all the reactants and products, they have some stoichiometric coefficients. So 6 into, so you need to multiply it with that, like multiply standard heat of formation with this coefficients. So delta H CO2 into 6, okay, plus 3 delta H H2O minus 15 by 2 delta H O2. Now for O2 it will be 0. Okay, so you should always keep in mind, since O2 is the elemental form which is available, like the form which is available in nature, for O2 this will be 0, minus delta H C6 H6. Okay, so 6 into minus 393.5 plus 3 into minus 285.8 minus 48.6. okay, check whether all the units are same or not. So if I solve this, then the answer will come out to be 3267, like minus 3267 kilojoule per mole. Now moving forward to the next question. Calculate the change in enthalpy of reaction carried out in a bomb calorimeter for combustion of 1 mole of cyanamide for the following reaction. Okay, so here again you need to find out delta H minus delta, no sorry, you need to find out delta H. Okay, now here the heat of reaction or the internal energy is given. Okay, and the reaction is carried out in bomb calorimeter, which means that it is performed at constant volume. Now delta H is related as delta H equals to delta U plus P delta V, and again like this will be minus 742.7. now P delta V, as I have discussed in earlier slide, it will be written as delta N RT. Okay, so minus 742.7. Now delta N for this reaction, consider only gaseous components. Okay, so this will be 1 mole of N2 plus 1 mole of CO2 minus 1.5 moles of O2. So this will be nothing but, since this is in solid form, you will not consider this. So 2 minus 1.5, which is nothing but 0.5. So this will be plus 0.5, 8.314 into T is 298. Okay, so since this is in kilojoule, divide this by 1000 because this units are in SI, which will give me energy in joules. So if I want to convert this joule into kilojoule, divide it by 1000. Okay, so the answer will come out to be minus 741.46 on solving this. Okay, so yeah, that's it for today. So now I can thank you for joining. Thank you for this session. I will stop sharing my screen and I will end this meeting. Thank you everyone.